Hello, in this lecture we're going to discuss a part of Chapter 8. Specifically, we're going to look at some definitions, some mathematical definitions of symmetric, skew-symmetric, and orthogonal matrices. So if we just go to the basic definitions, we have three things here. So first of all, we're going to assume our matrix is denoted as A in bold. And this needs to be a square matrix for these definitions. So the matrix is square, and basically it is a matrix consisting of real numbers. So it's a real square matrix. It's defined as being symmetric if when you transpose the matrix, you get the matrix back. So in other words, if the matrix and its transpose are equal, then it is a symmetric matrix. It is skew-symmetric if when you transpose the matrix, you get the negative value for each element. So each element of the transposed matrix would be the negative of the original matrix. And finally, it's orthogonal if the transpose of the matrix is equal to the inverse of the matrix A. So here are just some examples that show a symmetric matrix, a skew-symmetric matrix, and an orthogonal matrix. And obviously the way you would verify that these are true would be to do the operations listed here under items 1, 2, and 3. So doing the operations and proving whether or not they are true will determine whether or not the matrix is symmetric, skew-symmetric, or orthogonal. So it's kind of an interesting thing that any real square matrix A, any real matrix, can be written as the sum of a symmetric matrix R and a skew-symmetric matrix S, where R and S are defined as follows. So the symmetric matrix would be 1/2 of A plus its transpose, and the skew-symmetric matrix would be 1/2 of A minus its transpose. So we can look at an example here where we have a matrix A. If we construct by taking A plus A transpose times 1/2, we construct R, and then we construct S. We can see that this theorem or this expression is true. All right, so now looking at a couple of theorems. First of all, the eigenvalues of a symmetric matrix are always real, and the eigenvalues of a skew-symmetric matrix are pure imaginary or zero. Now we want to talk about an orthogonal transformation. So an orthogonal transformation, y is equal to ax, where A is an orthogonal matrix. So our original matrix was x, and then it's going to get, and here as you see, it's a column matrix. So we have x1 and x2, and then in this example, this matrix of trigonometric functions is an orthogonal matrix, and we're basically doing a transformation to get the column vector or the column matrix y. So A has to be an orthogonal matrix, and what this does is this essentially rotates in space the column vector x1 and x2 to give you a new y1 and y2. So if you can visualize this in 2 or 3 dimensions, it's basically a rotation. And here we have 2 dimensions because we have x1 and x2. Basically what this does is that takes x1 and x2 and that rotates it through an angle theta. There are other types of orthogonal transformations. Orthogonal transformations are important because they allow us to take a set of variables, do a transformation that connects those variables more to the real world that they represent. So for example, if you had a pulley or a spring and mass on a table, and it was oscillating back and forth, and it was at an angle to the dimension of the table, and you defined one direction of the table as x and the other direction of the table as y, then you would have a really complicated set of equations that would describe that rotation. On the other hand, if you could rotate your Cartesian coordinate system in such a way that one of the axes aligned with the direction of oscillation and the other had 0, you've basically found the principal components. So you can accomplish that through an orthogonal transformation, and the reason we do it is that sometimes it allows us to represent deterministic systems in a much easier way, as well as stochastic systems too, but the best example I can think of is a physical one. So you can show, as I said in the previous slide, that any orthogonal transformation excuse me, in the plane or in three-dimensional space is a rotation, possibly combined with a reflection along a straight line or a plane. And the main reason this is important, so let's go to the next slide. The main reason this is important is that an orthogonal transformation preserves the inner product. So if I have two vectors A and B, if they undergo an orthogonal transformation, then the inner product A dot B is essentially the same under an orthogonal transformation. So it preserves the length of the norm of any vector as well. Now the reason this is important is that if we are going to do an orthogonal transformation in such a way that we're representing either coordinate systems or a set of variables in a different way, and this often happens, and this actually can be more than three-dimensional. So, for example, let's suppose you have 10 people speaking in a room, and you have 10 microphones, and the signal that you're recording is a signal in 10 microphones. So that would be a linear combination of all the speakers in the room. It's possible to find an orthogonal transformation that can take that signal and actually divide it into the signal originating from each speaker. Now, what you don't want to do is you don't want to influence things like the relationship between speaker 1 and speaker 2, and you don't want to influence the relationship between sensor 1 and sensor 2, and you don't want to change the physics when you do that transformation. So orthogonal transformations that preserve the inner product basically are only doing things like crazy rotations so that your coordinate system is more convenient, even if it's more than a three-dimensional coordinate system. So this actually turns out to be extremely important in electrical engineering for a number of reasons. Okay, and then finally, we have a theorem relating to orthonormality. So a real square matrix is orthogonal if and only if its column vectors and also its row vectors form an orthonormal system. So what that means is that if you have row 1 and row 2 and you take their inner product or their dot product, you will get 0. But if you take row 1 and you take its dot product with itself, you will get 1. So the use of orthogonal matrices, basically what this is saying is each row and column represents something completely linearly independent. So, if you think in space, for example, your x coordinate is always independent from your y coordinate, which is always independent from your z coordinate. There are three orthogonal directions, and if you want to represent something as a vector and you use like the I hat, j hat, k hat, then basically what happens is your vector is orthonormal. That unit vector is orthonormal. It has a length of 1, and that means that you don't change the relationship between your variables.